In regard to your do now, you've got an equation up there that is balanced, and it says if the concentration of copper 2 ion, which is a product, is increased, E cell will decrease because the forward reaction is opposed. All right, you're increasing the concentration of a product. Well, it's a little bit tricky, and in regard to a POGIL packet that I have for you, they ask for explanations in regard to Le Chatelier's principle, and previously we were told, oh, that's great, let the kids do that. And then we were told, well, you can't use Le Chatelier's principle because this isn't a reversible reaction. So that's why it's safer to say, as this concentration increases, the forward reaction is opposed, and as a result, E cell decreases. You will note I no longer have the not sign here because if you increase this concentration, it's going to be greater than the 1 molar standard concentration. There's another way to explain it, and that is through the Nernst equation and Q, and that's what we're going to open up with today. Now, I sort of watched a webinar last night in between watching the very good tennis and playing with Gabe. So I've got to go back and review that. And he's claiming he's a table leader actually. He's saying, oh, you can explain it any which way you want. They'll take it, after we were told no. So I'm a little confused there, and I'll go back and take a look at it. There were just too many other things last night. The other question here is, you will see that I listed the anode as copper. Why is the anode copper? So you've got copper to copper 2+, so copper is being oxidized. Oxidation occurs at the anode. Now the anode has to be a metal strip, so it's never going to be an ion, and you'll see that in your 4.1 pre-lab, and that's a common mistake that kids make. The cathode cannot be iron. Why? Well, the reduction reaction is the iron 3+ to iron 2+. You're gaining an electron. But you don't want to generate iron, so you can't use iron as your electrode. Here's a case where you've got ionic species, if you will, so you need to use an inert electrode such as platinum. Don't think it'll come up, but it was a good equation to make that point clear. All right? So the cathode would probably be platinum. Say it again. The reason why the cathode is not iron, neither of these is solid iron, right? This is iron 3 ion and iron 2 ion. So they're both aqueous. Yeah. So in that case, the metal electrode would be a different metal, something inert, such as platinum. Platinum has very low activity. All right? So that's your do now. Now, in regard to this explanation, we just want to make this point a little bit clearer, and it is very mathematical, so I think it's something that you'll actually enjoy. And of what I did listen to last night and what did sink in, you know, they asked, well, where do kids go wrong on the AP exam? And the guy said the kids just have terrible difficulty explaining anything. And I don't think that's your case. I think we've had so much justification, explain, explain, explain. And you see it, I mean, how much have you seen it on the quizzes? It's ridiculous, but that's why you're going to do well. One of the many reasons you'll do well in May. You're also really smart, which helps. All right. The Nernst equation's kind of interesting here because they took the equation off the exam. Not on your formula sheet anymore. So why should we use it? And then all of a sudden it popped up. This equation relates cell voltage for non-standard conditions. This is when you alter the concentration or the pressure if you're dealing with gases. So now you have E cell. To a standard voltage, E cell not, where you've got 1 molar concentration or 1 atmosphere or 1 bar of pressure if you're dealing with a gas. And you're going to relate this to the concentration of reactant and product species, aqueous and gases only. That's going to be related through reaction quotient Q. And again, when you deal with reaction quotients, you typically have an equilibrium, or, well, I guess you don't. For KEQ, you're at equilibrium. For Q, you've altered equilibrium in some regard. But if you were to look at Q here, Q would be the concentration of product ion raised to their stoichiometric coefficients over concentration of reactant ion and gas. So why did I exclude poor little copper? Good. All right, so we're going to find a way to relate all of these terms together, and this is going to occur through the Nernst equation. And that equation is shown here. And you're like, but how am I going to possibly remember that? Let's take a look. We know that delta G is equal to negative NFE. And that's why in a voltaic cell with a positive E cell, you're going to have a negative delta G and you're thermodynamically favorable. We also know that this is equal to negative RT ln of K, KEQ, like we talked about the other day. So basically you have NFE is equal to RT ln of K. So if you solve for E under standard conditions, you'll have RT NF ln of KEQ. Okay? So now what happens is if you make an alteration in some way, then E cell is equal to E cell naught minus RT NF ln of Q. Now, if you have some reaction, and let's assume you've got an ion here and an ion here, just for simplicity, Q is equal to the concentration of product species over reactant species. What is ln of 2? .693. What is ln of a half? Okay. So what's ln of 1? 0. So ln of a number greater than 1 is positive. Ln of a fraction between 0 and 1 is negative, correct? Okay. So in the example we looked at previously, we increased the concentration of a product ion, correct? So in doing so, we essentially generated a number greater than 1, and the Q was positive. And we then subtracted this from E cell, and we saw that E cell decreased with an increase in product concentration, or truthfully a decrease in reactant. And I'm sorry, I started to write something quickly, so this is with N. I hope it's clear. Now, in contrast, had we increased the concentration of reactant, Q would have been a fraction. So ln of Q would have been negative. We would have put a negative in here, and a negative times a negative is a positive. So we would have been adding to E cell. So E cell increases with an, well, let's fix that. With a, didn't make it any better, with either a decrease in product concentration or an increase in reactant concentration. And that'll hammer your explanation home. But I'm going to do some further research. I still like increase in reactant, forward reaction is favored, increase in product concentration, forward reaction is opposed. So let me do a little more, but the Q will nail it for you. So E cell decreases with an increase in product or a decrease in reactant because Q is greater than 1 and ln of Q is positive, which is subtracted from E cell. And then in this one, E cell increases with the alternative setup, either a decrease in product or an increase in reactant, because Q is a fraction between 0 and 1. So ln of Q is negative, which is subtracted from E cell, hence the increase. All right? Yep.
How do you know you're increasing the reaction enough to the reactant enough to make it a fraction between 0 and 1?
Initially, the concentrations are all 1, so any increase will do it. And when I say 1, I mean 1 molar, or 1 atmosphere of pressure for a gas.
So is the effectiveness of any E cell really E naught cell minus RF over, or RT over NF times ln Q, but since 1 over 1 is 1, and natural log of 1 is 0, it doesn't affect it?
Correct. All right. In regard to the other information here, you're not going to be asked to calculate this anymore, so we're not going to. So in terms of the Nernst equation, for us, it's only important in regard to Q's effect in determining E cell, so we're not going to do this. And this is a non-calculator based problem. Let's take a look at it to make sure we can do it. So under standard conditions, the concentrations are 1 molar for the ions. The standard reduction potentials are provided. You can see that copper is being oxidized and silver ion is being reduced. So what's the cathode? Silver. Silver. The substance that's being reduced is silver ion. The cathode is the metal, which would be silver. Okay? Calculate E cell. This is a voltaic cell, so E cell is? Got to be positive, so what are you going to subtract from what? It's going to be 0.80 volts minus 0.34 volts, which is 0.46 volts, correct? if the concentration of silver ion is increased, what happens to the value of E cell? It increases, the forward reaction is favored, and what's the other key part with Q? Q will be a fraction, which has a negative value when you take the ln, which gets subtracted from E cell naught, and as a result, E cell increases. You've got it. So that's the justify piece. The only other thing I could think of, it says identify the cathode, and the other thing they could ask, and I have seen asked previously, is does the mass of the cathode increase, decrease, or remain the same? Why does it increase?
Because it's changing from aqueous solution back to solid.
Because you're generating the solid. You're generating it. So the mass of the anode would decrease because it is being consumed. It is a reactant. And that came up on the 2014 exam. So those are the types of questions. Now, in regard to the multiple choice questions for electrochem, don't see too many of them asked over the years. But they hit it very hard in part 2 in 2014 and 2015, not as hard last year, which is why I gave you that one to do over spring break, because we hadn't finished everything. So not this weekend, but probably the following weekend, you'll have a different exam to do, and there will be a lot of electrochem on it. And the thing with electrochem is it's the last unit taught, and I feel badly for the northern schools that don't, they're 3 weeks behind us in terms of time in school already, because when I went to school up north, you were in school till the end of June. And, we're already 3 weeks into break by the time the kids graduate. Like my high school graduation was the end of June on the football field in 95-degree weather. But in any event, so they often don't get to this. And that's why it's so much to your advantage that we are finishing today with 5 weeks to review. All right? Okay. In regard to concentration cells, there's really not much there. You just have different concentrations. And other than that, there's nothing you need to know, so we're not going to play there. We're not going to cover pH measurement.
Wait, what page is it?
So my pages may be slightly different because I threw some more pictures in. So we were on page 10. You can skip all of 11.
Are we not doing concentration cells?
Nope.
Okay.
I have a question about
Go ahead.
more the math. The silver didn't have an S next to it on the product side, so you just need to.
But yeah, silver's a solid.
Okay.
And it may just be a typo. Hang
What
on.
else do we skip?
Yeah, just slot.
Okay. Concentration. We
But
see
you know silver's
we
a
see
solid.
all of 8 and all of 9.
And
And 10.
yeah, and then we're not going to cover the pH meter. There are all different types of batteries. You know that anyway because you know about your cell phone batteries. You know about, the new lithium. What's in your cell phones? All right, and then just regular batteries or alkaline batteries. But they have some newer ones that are supposed to be better for like Wii and Wii remotes and your Xbox remote. Well, we put rechargeables in there because otherwise we would just be going through batteries like crazy. But you know that there are all different types of batteries. You know about car batteries, etc. We're not going to talk about corrosion. All this stuff is very interesting, but it's just not what we need right now. There's a little YouTube video here. We can take a look at it at the end if you want. It's just the crash course review, and it just goes over a lot of little pieces. So it may be worth looking at in a little while. All right. The other piece we want to talk about today is electrolytic cells. And there are a couple of major differences between electrolytic and galvanic cells. First of all, with your galvanic cells, you know that E cell is positive, delta G is, and so this is thermodynamically favorable. Your chemical reaction is all you need to get the reaction to go, as well as the salt bridge. With electrolytic cells, your E cell is going to be negative. Your delta G is positive. So these are not thermodynamically favorable cells. And these will require some type of power supply. You can use a battery. Lots of things you can use, and we'll take a look. Rechargeable batteries fall under this category.
Can you use a galvanic cell to power an electrolytic cell?
It may not provide enough power. Well, you can couple reactions together, but I don't know if this would be an example of coupling. I don't know. Good question. Find out the answer. All right. So what you're going to see here is an electrolytic cell is going to use electrical energy to generate chemical change. Previously, we were using chemical energy to power it up. You're going to have an electric current from some source. You've got a thermodynamically unfavorable reaction, and there are a lot of different examples here. Now, this is not in your notes, nor is the other, because when I went through period 2, I thought about it. I'm like, I said the stuff, but I'm not sure that it was clear enough. So I'm hoping this will clarify it, although maybe you didn't need it. So here's the power source, and right away you recognize it as an electrolytic cell. And the one problem I ran into was back in 2007, when you were still tiny.
Maybe you were. What?
But this would have been 10 years ago. You guys were little. I didn't understand, and I'll be honest, I didn't really harp on electrolytic that much. To me, it was pretty straightforward. But I couldn't believe it when my kids came in and told me 48 hours later that they had a galvanic cell in part 2. And I looked at the question, I'm like, that's not a galvanic cell. They're like, of course it is. I did this minus this, and I just couldn't believe it. Because what do you see? Power supply. But there were other clues as well, and they just didn't see it. And we'll take a look at this later on. But they just didn't see it. You can electroplate a spoon. That's how you get silver spoons, you know, for babies. Just whatever baby needs is a silver spoon. I'm not going to go through the whole process right now. You can, for the rechargeable batteries, this is a way that aluminum is generated. You can plate things with chrome. I have a feeling that, like the white gold, mine needs to be redipped. But if you, I know my rings are very little. But if you look at these are the white gold, and they get rhodium plated like once a year because they start to look yucky. So I give them to the jewelry store and they rhodium plate it. But that's also, what?
That's how they do it?
Yeah.
That's cool.
Yeah.
Jewelry. They had AP jewelry at some point in school.
Oh, yeah.
Really?
We had a bathroom.
AP cooking.
Yes.
All right.
I need
So
that.
cool.
I need that.
They have it at Boca.
What? I need to learn
AP
cooking.
Yeah, APE.
Yeah, you would
AP
learn how to
cooking? I would get 5.
During the break, I'll tell you about one class we had at Cornell that is just, I didn't take it, but my boyfriend in college took it, and he really liked it. I'll tell you about it during break.
My friend got me.
Exclusive.
I do so
All right.
What is this sleeping? Oh.
All right.
Man, I would take a sleeping class.
No sleeping classes. This is a smart class. All right. This is going to seem a little bit choppy. Give it 5 minutes. I promise you'll be good. Alrighty. For example, you can have molten sodium chloride. Oh, you can have molten sodium chloride, which is sodium chloride in the liquid state. You can generate sodium in the liquid state and chlorine gas. And you'll use a battery to pass electricity through this substance. The oxidation reaction is shown, the reduction reaction is shown. And this will make a little more sense when I show it to you in aqueous solution. But basically, if you have sodium chloride, you know that came from a sodium ion and a chloride ion. And you could then predict the oxidation and reduction reaction. I'll come back to that in a little bit. You don't need to know the positive versus negative charge anymore. This is not in your notes. I actually found this in a different textbook. And what I liked about it is, look, what does that battery represent? The power supply, and therefore it is a, what type of cell? Electrolytic. All right? So what's happening here is that you are generating chlorine gas. You can see the bubbles. And you are generating sodium on this electrode. And you can see the sodium building up here as well. Now this piece is a little bit tricky, but you'll be very good at it. When you dissolve a substance in water, you get an aqueous solution. So if you had something like aqueous sodium chloride, you know you're dealing with sodium ion and chloride ion, the gain of electron, the loss actually of 2 electron to generate chlorine gas. So this piece of the puzzle is very obvious. But if you have aqueous solution, you also have to break up, if you will, water. And you can see the electrolysis of water shown here. Now I'm showing you the oxidation reaction and the reduction reaction. If you were given reduction potentials, you would only be shown reduction reactions, and I'll show you that in a minute. But the electrolysis of water has a negative E cell because we have electrolytic negative E cell. What evidence would one see that products are generated? What would you be able to observe from this reaction?
The water level going down.
Decrease in water level and bubbles. You observe bubbles representative of a gas. So what happens when you have a mixture of ions? For example, let's say that a solution contains a mixture of these 3 ions. You'll have a low voltage and then it'll increase. And you want to know the order in which the metals plate out on the cathode. Their reduction potentials are shown. The approach here is that you'll consider the oxidation and reduction half reactions that might occur, and you'll select the one at the lowest voltage, a negative value closest to 0. That right now makes no sense. It says the more positive the E value, the more the reaction has a tendency to proceed in the forward direction. And that's the one that will plate out first. So silver will plate out first, then copper, then zinc. The greater the E cell, the faster that substance will plate out if you were trying to separate them. There's an example in your textbook I want to take a look at, and again, this is not going to stick until we combine it with the water concept, so just patience, which I know is hard, especially for a New Yorker. All right. And I'm just going to change the wording in this ever so slightly. Trying to block the answer. Except my sticky note is yucky. Probably can see through the paper anyway. All right, whatever. Here we go. Now I gotta hold this. And just a mouse. Hey, what was that?
Press cancel.
Oh, no, no, no. That's because I dropped the mouse on the floor. It'll stay there for a few minutes, won't it?
You press cancel.
I know, but I dropped it on the floor. All right, now I'm good.
Use
It's
your
good.
keyboard.
Oh,
Dash,
that's too
dash.
dangerous. Did you press save?
I pressed don't save. Doesn't really matter though, because I didn't change anything as we went, right? Okay,
Not really.
I did.
Oh, it's on video.
No, did I change anything in my notes?
You change the solid.
I put the solid in. Okay.
It's also on
Oh, you
video.
type a question in. Yeah.
What's the mass? Oh yeah, the mass.
Oh, yeah,
It's
yeah,
on
yeah.
video, though.
I know, but do you think I'm going to go back and watch it?
I'll rewatch it.
All right.
Oh,
Here we go. It says an acidic solution contains blah, blah, and blah. Using the E values listed, which are right here, give the order of oxidizing ability means which is most likely to be reduced, and predict which one will be reduced at the cathode at the lowest voltage. Do-do-do. Which one has the greatest E cell?
Cesium.
That's not cesium, that's cerium.
Yeah.
So it'll be this one, then that one, then that one. That's it. They don't. They don't have the names.
Well, we don't have to write anything, so it's okay.
Right, you could just write the other, that's true.
That's generally what I do.
Safer, I guess.
Unless they actually ask you to do that.
No, I had made, oh, they're still there. All right, I'll fix the other things after. So let's link it together now, and now you'll see where that comes into play. And this, I think, may be overkill, to be honest. I think this is probably too much, but we'll walk through it. All right, so here we go. Caution with electrolysis. If you have sodium chloride in the aqueous state, it will make solid sodium and chlorine gas. What is listed here are 4 reduction half reactions. Which reactions should be oxidation reactions?
Sodium.
The sodium ion plus electron is good because in sodium chloride you'd have sodium ion and chloride ion. So this reaction's happy. This reaction I should flip because I want chloride ion to be a reactant. Does that make sense?
Right.
Yes? Why should I flip this reaction? I want to show the breaking up of water. So I'm going to flip that one as well. And this one's fine. So I want water as reactants. I want the ion, sodium ion and chloride ion, as reactants as well. The way I calculate E cell is exactly the same. It's the cathode minus anode. And regardless of how I do it, I will always get a negative E cell, which is what you would expect for an thermodynamically unfavorable reaction. Here's the key right here. The reaction most likely to occur is the one with the least negative value of E cell, because it would require the lowest applied voltage from the external energy source. You don't want to waste, so you want to use the lowest energy, the lowest voltage possible. So what I've done here is I've grouped together the two oxidation reactions. Those are the two flipped ones from here. We discussed why we flipped them. And now I'm looking for the combination that gives me a negative E cell as close to 0 as possible. So of the two reduction ones, they're both negative. I'm picking the one closest to 0. Of the two oxidation, they're both positive. I'm picking the one closer to 0. And I'm going to do cathode minus anode, and this is my E cell. The delta G would be positive or negative? Positive, always for an electrolytic cell. Yes.
So you're trying to get it closest to 0?
It's going to be negative. You want it as close to 0 as possible, so you use the least amount of voltage from that power source.
Because it would take more voltage to take the
It'll take more,
electron.
yeah, the other one, it's exactly. This is kind of like a funny reaction. You would expect that hydrogen gas would be generated as well as oxygen gas. But it's a little complicated and we're not going to go into it. Look at this example. It says predict the electrolysis reaction when silver nitrate is electrolyzed using platinum electrodes. So again, I know that silver ion has to be a reactant. So this reduction reaction at the cathode is good. This is showing the hydrolysis, the breaking up of water, and this is showing reduction as well. So those are my reduction reactions. It turns out that you cannot oxidize nitrate ion. You're not going to get that one, so don't worry about it. The maximum oxidation number of nitrogen is +5, and that's what it would be in the nitrate ion, so you wouldn't go higher than that. Here's your other reaction. And if you were looking at this combination here, cathode minus anode is going to be negative, but you want it as close to 0 as possible. So which of these will you use? Top one. So this minus that gives me this. So the reactions that we're using are this one and this one. So what gets generated? What are your products? What might you see? Gas bubbles from oxygen and mass of silver would increase. Exactly. Try and do this one. I'm not going to highlight it because it's harder to see. It looks hard, but it's not. It's going to be very obvious to you. Think about what ions, where the ions have to be. Think about where the water has to be.
2H2O plus 2 bromide ion produces 2 hydroxide ion, hydrogen gas, and then solid bromide.
Is that what you got? Yes, yes? No, no? Okay.
That was it.
I didn't write all the equations down because I sort of figured out which ones. The other one had this. So this had to be the anode. So in regard to the cathode, I had this and this. So they're both negative. You're going to go for the one closer to 0. And then do you want to subtract this from it or this from it to get a negative number closer to 0? You want to subtract this. So it's going to be this minus that, which means this reaction is correct as written. So I'm going to drop the water down. The hydroxide ions and the hydrogen gas are going on this side. I've got to flip this reaction. Oh, I already flipped it. I must have flipped it already. So this is here, and this is here. And this is a liquid, so you'll get a brownish reddish color in there, and you're also generating hydrogen gas. So you would see bubbles. You're also generating hydroxide ion. So what happens to the pH? It increases. But I think this is probably overkill for May. Yeah, it's not terribly difficult, but I was reviewing the learning objectives, and I'm always hesitant to pull stuff out of the curriculum because then they'll like put a question on it, but that to me is probably overkill. And you've got 1 or 2 problems on it on your practice quiz. You'll nail it down. I'm not worried. All right, the very last piece for the year is stoichiometry based. It is very easy. Right, just like where we started. I know you're really tired. It'll take about 8 to 10 minutes, and then we're done. For the whole year. Forever. Let me put it this way. There's no more new information. All right, last piece is quantitative electrolysis. We're going to link electrolysis, and not the hard part, to stoichiometry. Super simple. Established by Faraday. You already know Faraday's constant. We can show that the amount of reactant consumed or product generated during electrolysis is related to the molar mass of the substance, the quantity of electric charge used, and the number of electrons that are transferred. You know how to figure out electron transfer. You know how to find molar mass of a substance from the periodic table. The electric charge will be new. For those in physics, you probably have a slight advantage. The only formula that we have yet to discuss this year on your equation sheet is this one. I call it the quit formula. The quit. No, because it's Q is equal to I times T. So I is the current in amps. Q is the charge in coulombs. Remember we talked about Coulomb's law with the plus Q and the negative Q? Over the time in seconds. We're going to link this formula now to stoichiometry. There is a strategy to determine moles or mass, and that is indicated here. I think we're just going to let it rip, and you'll see it's very, very easy, but the strategy or steps are indicated at the top here. It says what mass of gold will be deposited at the cathode in 1 hour by a current of 1.50 amps. This equation would have to be given because you don't know what the charge of gold is. Gold has a variable charge. It's a transition metal. First thing we're going to do is calculate Q. Q, the charge, is equal to the current in amps times the time in seconds. The amps were given. They gave us 1 hour, so we're going to convert that to seconds. We'll multiply the 2, and we have 5.40 times 10 to the third coulombs. From here, it's just a stoichiometry step problem. You're going to go from the charge to moles of electrons using Faraday's constant. The coulombs will cancel. Now you're going to go from moles of electrons to moles of substance. For every 1 mole that is generated, 3 electrons are utilized. And then you convert to the mass in grams. You also want to be able to run it backward, and we'll do them both ways. The next example is grossly similar. Let's do it step by step. Now this is something they have definitely asked in the past. What mass of aluminum, so we're looking for the mass of aluminum, will be deposited at the cathode. The time is 50 minutes. And the current is 2.00 amps, and that's I. Remember, Q is charge. We're going to go after the Q, I times T, and that's going to be 2 amps, and you've got to be in seconds. So 1 minute is 60 seconds. So that's 3,000 seconds. So that's going to be 6,000 coulombs. Now I usually do that part separately. I think just because it's, as a chemistry person, this to me is more physics-based, and it's a little foreign for me to do it with stoichiometry, so I usually process that piece separate, but you don't have to. For every 1 mole of electrons, I have 96,485 coulombs. For every 1 mole of aluminum, how many moles of electrons would we have?
3.
Why would it be 3? Because of the charge. You got it. You know what the charge of an aluminum ion is. I shouldn't have put a line through that. I meant to put it through the C. Sorry. And 1 mole of aluminum is 26.98 grams of aluminum. And that's going to be 0.5 59 grams. Not bad.
So when you do this, is it one like solid piece of metal at the end? Like when it gets dotted on it?
Yeah, you wouldn't really scrape it off unless you had an inert electrode, then I guess you could scrape it off.
Is the 96,485 on the
Yes.
sheet?
Yes, yes.
Yep.
I'm going to do these 2 problems in reverse. The example, well, it doesn't matter. We'll just do it straight up. In regard to the example, this is the type of thing you could do without a calculator. so we'll work through it. It says, which of the following solutions would yield the greatest mass of metal at a platinum cathode during its electrolysis? You have the same current of 1.50 amps and the same time of 30.2 minutes. So the Q is the same for all of them, right? Why? Because you have the same current and the same, okay. So the Q is the same for all of these. And you've got copper 2 plus, because you have copper 2 sulfate, silver nitrate, and you've got gold 2 plus, because you have gold 2 chloride. And the Qs are all the same.
Like, you move your paper around.
So this step is the same, right? 2 plus. That's what I said and not what I wrote, right? Oops, thank you. You know, it's funny, I don't have gold listed as a 2 plus oxidation number either. Okay, so this is all the same. Now here's where they're going to start to differ, right? Because we're going to have 1 mole of copper to 2 moles of electrons. This will be a 1-to-1 ratio. Why? You got it. And then they're going to differ here too. Be careful though, because you have to take this into account too. So copper's about 64 grams, right? Silver's about 197. And gold is? Do I have this backward? I'm sorry, I have them backward. This is 108. Should have peaked. And the other one's 197? Okay. Is that legible? Is it beautiful? We'll make it better. Just like my Federer who won yesterday. All right. So, what's going to make the greatest mass? This is just going to be a multiple of 32. This is going to be 108, and that's going to be half of that, less than 100. So this is the winner. And then the very last new problem of the year. This is going to be in reverse. Are you good here? This is a happy problem. The very last problem of the year says how many amps. So you're looking for what?
Q.
You're looking for I. The mass, yeah, then that'll be what you find last is Q, and then you'll use it. Yeah. You want to get the mass? No, the mass of magnesium is given. We've got molten magnesium chloride, and the time is 2 hours. Go. For magnesium, really, 24.305. Sillies. Just be careful, you're working upside down here. Let your units drive your problems. Now, if you can chain the whole thing, great. I'm too stupid. What'd you get? What'd you get? Cool. This concept to me, they could hit you on, and they haven't done it in a while. Understanding that you need a power supply for an electrolytic cell, that you have a thermodynamically unfavorable reaction, therefore delta G is positive with a negative E cell, is the key to electrolytic cells. Okay? The lab will involve making galvanic cells. You'll have different reactions using different metals. It's really very fun, a little bit messy, and we just need to decide whether we're going to do it Friday or Tuesday. The lab only takes about 50 minutes, so that would still leave us with that time to review, and we'll argue about when we should have your quiz. Questions here? So this is it. This is the last new piece. Your AP exam is in less than 5 weeks, so we've got to start reviewing like crazy.